Okay, thanks for the introduction. And hello, everybody. I'm Shota Yamada from AIST in Japan. And today I'm going to talk about our work on a unified approach to quantum key leasing with a classical-lessor. And this is a joint work with Fuyuki Kitagawa in NTT, Chahui Liu in Fujitsu Research, and Takashi Yamakawa in NTT. Thank you. Thank you very much for the invitation. And this work is on ePrint archive and also on archive as well. So this result is already public. Okay, so let me start with the presentation. Okay, so let me start with a motivating example. So let's consider a situation where Bob wants to go to a vacation. So during the vacation, he wants his secretary to deal with his emails. So Bob will lease so Bob leases his key to his secretary. So the secretary may use Bob's secret key to decrypt the ciphertexts that are sent to Bob during the vacation. So a secretary uses the secret key to decrypt the ciphertext and does some admin work on behalf of Bob. After the vacation ends, Bob is back. And after Bob is back, Bob wants his secretary to return his secret key to him. This kind of scenario also appears in subscription. A user is given a secret key during the subscription period, but if after the subscription period ends, then the secret key that allows the user to decrypt the contents will be revoked or should be returned to the service. So yeah, this situation happens in many situations. And however, this kind of task is impossible entirely classically, because if Bob leases a secret key which consists of classical string to the secretary, then the secretary can just copy the classical string and use it for future use. Even if secretary declares that he or she erases the secret key already, Bob cannot verify whether this is indeed deleted or not, because the secretary just copied the secret key and then declares that it is actually deleted. But in reality, secretary might keep the secret key secretly. So this task is classical impossible, at least without any update on the public parameter. However,
so before you go on, could you explain why it is not recommended or it's not desirable to update the public parameter? Because obviously an easy thing to do is to change the password once you return from the vacation, something like that. But I guess that's not.
Yeah. So I don't so it's always possible to change the it's not always possible, but it's possible sometimes to deal with this issue by changing the public parameter. But this sometimes requires the system to set up the new parameter again. And there is also another problem where the time differences causes the problem. For example, you revoke the key, but some user, for example, in the case of subscription, there is some slight time difference where the key is actually revoked, and this update of the public parameter is known to a user who encrypts the message or contents, for example. And so my point is that maybe the update of the public key will not be notified to everybody very soon. So there is a time difference between the notification of the public parameter update and the actual revocation. This is one reason why this is not preferable. And another reason is that sometimes it requires the setup of the system entirely. So I think that, to be honest, I don't think that I will show the quantum solution, but I don't think that this is a practical solution to this problem. But there is some advantage over these classical solutions, I think.
Yes, thank you.
Okay, yeah, thanks for the question. So, yeah, as I mentioned already, as I already mentioned, there is a quantum solution to this problem. And this is a notion called secure key leasing. And this secure key leasing comes with various flavors like public encryption, pseudorandom function, and digital signatures. In crypto system with secure key leasing, SKL, there are two entities, lessor and lessee. And the lessor gives quantum secret key to the lessee. The lessee uses this quantum secret key to do various tasks. In the case of public encryption, for example, this quantum secret key allows the lessee to decrypt the ciphertext. However, after some duration, for example, in the case of Bob and the secretary, when Bob returns from the vacation, the lessor wants lessee to return the quantum secret key, or at least lessor wants lessee to submit a deletion proof of destruction to the lessor. So this means that the lessee will not be able to use the quantum secret key anymore. So we want the lessee to submit classical or quantum proof of destruction that we call deletion certificate. And cryptographically, what we want for this property, is that this lessee will not be able to decrypt or decrypt the ciphertext anymore if the lessee submits the deletion certificate that is accepted by the lessor. In general, we want the lessee to lose the cryptographic capability after it submits the deletion certificate. In the case of PRF, for example, we want the lessee not be able to compute the PRF value anymore after the deletion certificate is submitted. In the case of signature, we want the lessee not be able to sign on any message after the deletion certificate is submitted. This is what we want for this primitive. And so this is a general framework of SKL, but we can consider a bit strengthening of this framework, where we enforce the communication between the classical lessor, between the lessor and the lessee to be classical. So this scenario is possible if the lessor and the lessee are connected via quantum channel. In such a setting, it's straightforward to send the quantum information to the lessee, quantum secret key to the lessee. However, we can consider a more restricted setting where the communication channel between the lessor and the lessee is only classical. However, even though their communication channel is classical, we want the lessor to send some information to the lessee so that the lessee can construct a quantum secret key. So this is what we call this is what we call SKL with a classical lessor. So you can see that the lessor is entirely classical here. And the lessee is still quantum. Actually, the lessee is inherently quantum because the security notion inherently requires quantum secret key or unclonable property. However, the lessor can be entirely classical, and the communication is also entirely classical. And this restricted version is more useful than the one with a quantum channel because of obvious reasons. For example, classical communication channel is much more stable and less expensive, easy to have. So we focus on this in this work. So here is the security definition of crypto primitive with SKL. For example, you can consider public key encryption, but the PRF or digital signature is also possible. So in the game, the security definition is defined by a game between a challenger and the adversary. And the challenger plays the role of the lessor, and the adversary plays the role of the lessee. And the challenger generates a private verification key for deletion certificate. So this is kept private. And at the beginning of the game, the challenger gives the quantum secret key to the adversary. This may be via quantum channel, and maybe this is via classical communication between the adversary and the challenger in the case of classical communication 1. But somehow the adversary gets the quantum secret key. And after the interaction ends, the adversary outputs the certificate for deletion to the challenger. And then the challenger checks whether this proof of destruction is correct or not. If it is not correct, then it aborts the game. But if it's correct, then it proceeds to continue the game. And the challenger will give the challenge to the adversary. In the case of the public key encryption, for example, this challenge is a ciphertext. And the task of the adversary is to decrypt the ciphertext to obtain the plaintext underlying the ciphertext. But you can consider other primitives like PRF or digital signature. And the adversary returns the answer to the challenger. In the case of public key encryption, this answer corresponds to the message. And the challenger finally determines whether the adversary wins or loses the game. We say that the adversary wins the game if the deletion certificate passes the verification by the challenger and the answer to the challenge is correct. In the case of the public key encryption, the answer should be the message encrypted under the ciphertext. And we say that this construction is secure if the probability of this happening is negligible. So this is the security definition.
The adversary can always answer wrong incorrectly. Right? You can choose to answer incorrectly, and this will always go to 0.
So your question is that how do we check whether the answer is correct or not? Or
No, I'm saying like adversary can choose to answer it incorrectly.
Yeah, the adversary chooses the answer incorrectly, but in that case, we consider that the adversary loses the game. In that case.
Yeah, we look at all possible adversaries. What you're describing would be one of the adversaries, but you look at all possible adversaries and want to say no adversary. if the scheme is such that no one was to win, then we.
Oh, okay, fine. Yeah.
Okay, so maybe I can give you a little bit more example. In the case of pseudorandom function, in the case of public key encryption, the challenge is a ciphertext, and the message, the answer should be the message encrypted under the ciphertext. So maybe the challenger encrypts a random message and sends the corresponding ciphertext to the adversary. And the task of the adversary is to decrypt the ciphertext to obtain the random message being encrypted. If the adversary is able to recover the message, then we think that the adversary wins the game. And in the case of pseudorandom function, for example, the challenge is random input. And when the answer should be the PRF evaluation result on this particular input. And we think that the adversary wins the game if the output of the PRF value that is guessed by the adversary is the correct one. In the case of digital signature, the challenge is random message. And the task of the adversary is to sign on it or forge a signature that is valid with respect to this particular message, which is randomly chosen. And the winning condition for the adversary is to pass the verification of the digital signature. Here I explain it a little bit in an abstract way, but actually we only consider public key encryption, pseudorandom function, and the digital signature. So this is the winning condition. Okay, so does it make sense?
Yeah, yeah.
Okay, yeah. So let me continue. So this is the security definition. And so you can consider a strengthening of the security definition. And the only difference from the previous one is that the challenger reveals the verification key after the deletion certificate is sent from the adversary. So this is the same game as the previous one, but the adversary, after the adversary submits the deletion certificate, if it's a correct one, then the challenger reveals the verification key to the adversary that has been kept private so far. And the winning condition, as well as the rest of the game, are actually the same. So you can consider this security game, and if the scheme is secure against this kind of game, we say that the SKL scheme has a VRA security, which stands for verification key revealing attack. And this security definition might seem a bit unnatural because verification key is revealed to the adversary, but this captures the natural definition of the security game where the adversary has an access to the verification oracle. Because if you give the verification key to the adversary, then this verification key will be used for simulating the verification oracle trivially. So this security definition may be something natural. Or maybe this is the way to achieve this natural definition of having verification oracle in a simple way. So this is a VRA security.
I have a small, possibly dumb question. Maybe you can tell me this if it's trivially impossible. What if the verification key is revealed before the decryption certificate is issued? Does the definition become invalid?
Okay, so you can consider a strengthening of the primitive where the verification key is entirely public, or it's revealed before the deletion certificate is revealed. Actually, I think that our construction doesn't satisfy this security definition, or at least I don't know how to construct it. And if you consider, for example, the public key encryption with this publicly verifiable version, this implies quantum money, and quantum money is much harder to construct than crypto primitive with SKL. So this may be almost the best we can hope for without introducing very strong primitives.
And is it the case that assuming quantum money, one can build it? Like, I guess you're saying one way, like if the the verification key was public, then you're sort of suggesting that it would imply quantum money.
Quantum money. Yeah,
But-
yeah. So maybe you can consider you can convert it into a public key quantum money if it is publicly verifiable. And how to construct a quantum money from it is to run the decryption algorithm and the public run the decryption algorithm of the PKE and the deletion certificate verification algorithm at the same time. So if you consider this combined verification algorithm as a verification of quantum money, then this implies quantum money.
And what about the other way? Is it the case that quantum money implies this
I haven't considered the other direction, but probably it's not immediately clear whether quantum money immediately implies this one, because quantum money is roughly speaking about the unclonability. But
Right.
what this requires is that you have this quantum state to be able to serve as a decryption key. So you need some functionality here. So I don't think that the quantum money immediately implies SKL primitives.
Thank you.
But maybe by introducing something stronger primitives like indistinguishability obfuscation or something, then this might imply SKL. But yeah, I haven't considered this direction.
Thank you.
Okay, so this is the security definition. And so let me explain our results. So in the regime of public encryption, we propose the first scheme that satisfies classical-lessor property and the VRA security at the same time. And this is based on LW assumption. So there is a work that achieves classical-lessor or VRA security separately, but this is the first time we achieve both simultaneously. In the case of PRF, ours is the first to achieve classical-lessor property. So this is the first time that the communication is entirely classical. But our construction also satisfies VRA security at the same time. And our construction is from LW assumption. Also, we also proposed the digital signature scheme with SKL, which is the first to achieve classical-lessor. And however, our scheme also satisfies VRA security. So both properties are satisfied simultaneously. And our assumption is LWE. So these are our results. And mainly, I think that I will mainly consider PKE as a primary example, but this can be possible to what I will explain basically is true for PRF and digital signature. Just for convenience, I will take PKE as an example. And these results are obtained rather by a unified idea. So we use the same machinery to construct these constructions. Even though the security proofs will be separately done, they are very similar. The constructions are very similar. So these are our results. So do you have any questions so far? Okay, maybe I will continue and yeah, take question whenever you have. So let me explain the idea of some previous work. KMY, which is by Kitagawa, Morima, Yamakawa, because basically our construction can be considered as an extension of KMY25 in some sense. However, the difficulty is that their construction doesn't satisfy the classical-lessor property, so they directly consider the quantum channel between the lessor and lessee. So main task of us is to replace this quantum channel with the classical channel to implement their idea. So I will explain the KMY25 framework first. So the starting point of KMY20, so the starting point of our work is KMY25, and roughly speaking, the main idea of KMY25 is to combine the watermarkable crypto primitive with BB84. So this is a one-line summary of their work, but I will explain it in more detail. So what is watermarkable primitive? In watermarkable primitive, one can construct a secret key that has watermark X embedded into it. So you can consider a secret key SKX, which has watermark in it. And this kind of a watermarked secret key can be computed from the master secret key. So you have a master secret key, and using this master secret key, you can compute a secret key that functions similarly to master secret key, but with the watermark embedded into it.
Could you explain how one should think about watermark in this context?
Okay, so let me explain this second bullet, and then I will explain more high-level idea. So, the property of watermark secret key, so the property of the watermarkable crypto primitive is that if you give SKX to the adversary, and later on the adversary somehow functions cryptographically, then you can extract the mark from the adversary. So, for example, in the case of the public key encryption, you consider the public key encryption PKX and the public key encryption, and you generate a secret key SKX, which embeds the watermark X, and you give the corresponding secret key SKX to the adversary. Later on, if the adversary is able to decrypt the ciphertext, which means that it functions cryptographically, then you can recover the mark X from the adversary X. So in high level, it means that you cannot erase the mark from the program unless you destruct the functionality. So you can consider the secret key SKX as a program, for example. And this decryption program or decryption device has X embedded into it. And if you try to remove the watermark X from the device, it's still not possible because of the watermark extraction probability, the second bullet that I explained. So, for example, you can consider this in copyright protection context, for example. So each of the decryption device might embed the watermark in it. And if you are a pirate, if you are malicious, you make the pirate version of the decryption device. But if you construct such a device, this has a watermark in it. At least from this device, you can extract the mark from it. And this mark might be identity of yours. So if you generate a pirate version of the decryption device, then this actually points to you by the extraction algorithm. So making the pirate version of the decryption device is not possible. So this is motivation of constructing this primitive and the explanation of this security property. Does it make sense?
Yes.
Yeah, it makes sense. So, but when is it possible? Like, what are the results about like existence of this kind of primitive?
Oh, so actually, you can consider various security definitions for this one, but it's possible. It's possible in the from very simple assumptions like public key encryption. So, for example, when you consider the public key encryption, so let me consider. Yeah, for example, you encrypt a message under two different public keys, and to generate a secret key for mark 0, then you encrypt then you generate a secret key for the first public key. And also, so you consider PK1 and PK2 and SK1 and SK2. So SK1 is embedded with the mark 1, and the SK2 is embedded with the mark 2. And the extraction can be done by changing the ciphertext. So if you change the ciphertext corresponding to PK2 a bit, but still you encrypt the same message under PK1, the secret key SK1, a user with the secret key SK1 is still not able to detect the difference because it only has a secret key for PK1. And so the extractor knows that the decryption still works, but it doesn't. If it doesn't detect the difference between the ciphertext CT2, then it concludes that this user is actually having this user actually has a secret key corresponding to PK1. So you can detect the mark 1 from the adversary. You can do similar thing in the second ciphertext. So you can fix the second ciphertext and change the first ciphertext. And if you if the adversary or decryption device doesn't notice the change in the first ciphertext, then you conclude that this device embeds SK2 into it. So you can extract a mark from it. So this is only a 1-bit example, but you can extend it to have a larger mark. So does it make sense?
Yeah. And the adversary, does he know himself to the mark X? If he has SKX with him or her, so can he see the mark, or how do I understand?
Oh, okay. So I was not able to catch the question. So would you say it again?
What did you say?
Yeah, sorry, the microphone is farther away from him, so I'll just repeat what he said. He was asking whether SK sub X is enough for the user to see X.
Oh, the user. I think that the user may or may not have access to the string X itself. Either is fine, I think. Oh, in this presentation, X is not revealed to the user, maybe. I think that this is not very relevant whether X is revealed to the user or not in our context.
But I guess in the deletion property, you want to remove X, right? So it couldn't possibly be classical.
Oh, deletion property. What do you mean by that? So what we want is that if you are given SK sub X, it's not possible for you to generate a decryption device such that you cannot extract X from it. So you cannot erase the information of X. So
Successfully. The way I was thinking about it was that I thought, okay, maybe you'll explain in the next slide, but I thought what you're going to say is that if I have watermarked the secret key with some X, right, and I somehow get to delete X, then I'm guaranteed by the watermarking property that you could not cryptographically use SK sub X. But I guess
Also,
something else.
okay, so yeah. So sorry, I didn't catch the question much. So
I don't want to, but continue. I just misunderstood something. That's okay. We can discuss it afterwards.
Okay. Yeah. So maybe yeah. So I will not talk about about how to construct this kind of primitive, but it's actually not very difficult to construct such an extraction, such watermarkable primitive that suffices for use our use. And yeah, so basically you can consider that this is a program that hardwires X, and it's not possible to change the value of X or remove the value of X. So this is an identity that is embedded into the program. Okay, so shall we continue? Shall I continue?
Yes, please.
Okay, yeah. Maybe we can go back to this later. But yeah. So basically, this is watermarkable primitive, and the idea of KMY25 is to combine watermarkable primitive with the certified deletion property of BB84. And yeah, so I will explain what is the certified deletion property in the next slide. So certified deletion property of BB84 is defined by a game between a challenger and the adversary. At the beginning of the game, the challenger chooses the information of the basis of BB84 and the encoded random bits. And then it generates the BB84 state that is encoded under the theta I and xi, like this. So if theta I equals to 0, then you encode random bit, classical string. But if theta I equals to 1, then you encode it in Adamar basis, plus or minus states. And these quantum bits are given to the adversary. And the adversary computes y1 up to yn, depending on some computation strategy. The adversary might do something and it gives y1 up to yn to the challenger. And later, the challenger reveals the information of theta 1 up to theta n and xi for the Adamar positions. So basically, the idea is that these y1 up to yn should be the deletion certificate or measurement result of the quantum state in Adamar basis. However, in this security game, the adversary might do something different, or the adversary can do arbitrary adversarial strategy. However, intuitively, this y1 up to yn might correspond to the measurement result of the BB84 state. And later, the adversary also outputs z1 up to zn to the challenger. So the certified deletion property of BB84 guarantees that the probability of this happening is negligible. So what is this probability? What is this event? In this event happens if xi equals to yi for all Adamar positions. And also xi equals to zi happens for all standard basis positions. So basically what this says is that it is not possible for the adversary to guess the Adamar basis measurements. It's not possible for the adversary to guess the measurement results of Adamar basis position in Adamar basis and at the same time guess the measurement result of the standard basis position in computational basis. So this is not possible or with more than negligible probability, and this is shown information theoretically. And if you look at this property, it is a bit similar to SKL security game. You can consider this is a kind of quantum key, quantum secret key, and you can consider this as a Y1 up to Yn as a kind of deletion certificate. And this is a this leaked information can be considered as a kind of revelation of deletion verification key. Theta1 up to theta n and xi for the all other malware basis position can be considered as a verification key for the proof of destruction. So there is a similarity, and this similarity is the starting point of KMY25 to achieve certified deletion property.
Sorry, this looks very similar to what I think was done in Bartuszek and Corano. Is it related to that?
Oh, this property, I don't remember who proves this property, but yeah.
Okay, we carry on. Sorry.
Yeah, I think that this is something well known, and yeah. So and this itself is not sufficient for achieving the SKL because you need the functionality.
Right. Right.
Okay. So yeah. And yeah, so this is the so yeah. This seems to be something closer to the SKL property with VRS security, because you even have a revelation of the verification key here, but this BB84 state itself is not a secret key that is useful for decryption or signing, for example. So you have to extend the state into something. So let me explain the KMY construction. So in KMY construction, they prepare the pair of public key and master secret key for all positions of BB84. And you apply the following map to the BB84 state using the master secret key. So here, this xi, which is an encoding of the random bit, is extended into xi concatenated with ski xi, where ski is the ith instance of the public key encryption, or this PKI, with the mark xi embedded into it. And if you apply this map for each of the position, what you get is the concatenation of xi and ski xi in the standard basis position, and something like this. This is a superposition of two secret keys, with the different mark being embedded into it. And the final quantum secret key will be something like this. This is a concatenation of SKI, all the SKIs. And to delete, you measure SK by other malware basis. So, and the verification can be done using the encoding information of X and theta. So this is the basic structure of KMY25. So you extend the BB84 state by this map. You have additional secret key register here. So let me explain the KMY security proof overview here. So the security, yeah.
So before you on the previous slide, what did you mean by apply the following map to the BB84 state? So I start with the joint BB84 state, and I add an additional qubit extended.
Yeah. So you start from the BB84 state. So and apply this map. So you have maybe superposition in the case of Adama basis position of xi's. And you just apply this map where xi is equipped with some additional ancillary bits.
Yeah, of course.
Yeah, and apply this map. So here what happens is that the watermarking functionality, watermarking algorithm is applied to these additional qubits. This is what is happening here. And you apply this map for each of the position of the BB84 state. Is it clear?
Yeah, for each x,
Yeah.
so for each x, we are concatenating the corresponding secret key with the watermark given by x, so that is fine. But I'm still not fully sure I understand the intuition about what we are trying to do by doing this.
Sorry again. So yeah. So
Yeah,
so
why is this the right map somehow? Like, I mean, I'm not able to even intuitively understand how.
why do we apply this? Why do we apply this map?
Now, what is the equation? Like, I wouldn't write this, right? So you must have had some idea about what you're doing to come up with this map. Is it clear? Intuitively, what you're trying to put here?
So the reason why we do this, I don't completely understand the question. So basically, the idea is to reduce the security to the watermarkable property. So that's why we do this. So we don't. So if we only care about the functionality, doing something like this is not necessary. But basically, the idea is to reduce the security of SKL to the certified deletion property of BB84. That's why we are doing this here.
Right. So somehow you're saying that you'll ask for the deletion, and then because X. Right. So you're somehow saying that if I ask for the deletion, then X would have certainly been deleted. This we can check, and then because X is gone, then the secret key would have become useless. Is that the way to think? No, probably still not. Okay, but please carry on. I think I'll figure it out for myself. I don't want to.
Sorry, and the SKIXI for different eyes are the orthogonal display?
Sorry again. So SKIXI.
Are they orthogonal for different eyes?
Oh, so how do we construct it?
Yeah, first of all, are they orthogonal and how do you construct them? For example, I could apply a unitary.
Yeah, we use the unitary. In watermarkable primitive, you have the map from MSK and X to SK sub X. And you apply this map to each of the bit of the BB84. This is what is happening here. MSKI and XI to this SKIXI map is applied to each bit of BB84, where you add some additional qubits. Does it answer the question? Hello, do you hear me? SKIX orthogonal. Oh, I think that this doesn't matter. So the question is whether SKIXI are orthogonal or not. I think that they may be orthogonal because they are just a classical string with different bits. But this doesn't matter much in this presentation, I think. Is it okay? Okay, so okay, thank you. Yeah, so let me continue. So this is the idea of KMY, and I had a doubt. Oh, yeah. So there is a question that asks whether the secret key is a product state or not. Yeah, this is a product state. So the final secret key is going to be the product state of it, or the smaller secret key SKI. After applying the watermarking, do we get an entangled state or not? Yes. The final secret key SKI is a product state of each of SKI. However, SKI is kind of entangled thing where the XI, the BB84 qubit is entangled with the secret key state. So there is no entangle across the different system like I. So I is the subscript for each of the position, but within the subsystem of SKI, you have an entanglement. So that's the answer to the question. Okay, so do you have any other question? So the second register is not mixed. I might be missing something. Seems like SK is a product state. So SK is a product state. So what I'm saying is that within SKI, you have an entanglement like this. But so let me put this way. So SK, the final secret key is a product state of SKIs. But SKI has an entanglement inside it. That's the answer. So okay. So yeah. So let me continue. So this is the secret key structure of KMY25. And let me explain the security proof overview. So basically what we are going to do in the security proof is to reduce the SKL security to certify the deletion property of BB84. So you assume an adversary that attacks the SKL security and convert it into a reduction that breaks the BB84 certified deletion property. And at the beginning of the game, BB84 state is given to the reduction. And of course, the goal of the reduction is to break the certified deletion property somehow. And the reduction generates the secret key using the map that I explained and obtain a quantum secret key. And this is given to the adversary. The task of the adversary is to break the SKL security. So it submits the deletion certificate. And this deletion certificate is converted into a deletion certificate of BB84 by some underlying computation that I will omit. And the challenger of the certified deletion security game gives the basis information. And this basis information is converted into the verification key of SKL. And the adversary, so after the verification is passed, the adversary can still function. Namely, in the context of the public key encryption, for example, it can still decrypt the ciphertext, even though it declares that it returns the secret key or it makes the deletion certificate. Even though it already gave the deletion certificate that correctly passed the verification, it still functions. So here we can use the watermarkable security property of the underlying primitive. In the case of public encryption, for example, the adversary is still able to decrypt the ciphertext, but you can use this adversary to get the corresponding marks embedded into the secret key. And this mark happens to be the BB84 information, XI in the standard basis positions. So this mark is submitted to the certified deletion challenger. So what happens is that because the adversary is able to generate the deletion certificate, then this can be converted into the Adama basis position measurement result, and this is going to be submitted to the certified deletion challenger. However, the adversary still has a decryption capability, so you can convert this adversary into so from this such an adversary, you can still extract the information of BB84 from the adversary, because the adversary is given a secret key that embeds the BB84XI information into it. So you can use this adversary to extract the information of XI and submit it to the certified deletion challenger. So if you have an SKL adversary, then you can convert it into an attack against certified deletion security. That's how the KMY security proof works. Okay, so is it clear? Yeah, so let me continue. Okay, so basically this proof works like this. And then let's explain our construction. So our starting point is noisy trapdoor claw-free families, abbreviated as NTCF. But in this presentation, I don't talk about the noisy version. I consider ideal version of it. Actually, the noisy version can be constructed from LWE, but for the simplicity, noisy, I will consider non-noisy version of it. And this is introduced by Mahadev and other work. So this is a very useful primitive for achieving classical communication in quantum settings. So this is very natural to start looking at it. And so in NTCF, you have two families of functions. Functions F, which are injective, and functions G, that is 2 to 1. And these F and G are going to be computationally indistinguishable. And we can, using these functions, you can generate a state of the following form: X concatenated with Y, where Y equals to F of X, namely X is the pre-image of Y. And this is possible in injective mode. And you can also consider the state something like this, where X register is a superposition of two pre-images of Y under G. And you can prepare these states without knowing which one you are given, F or G. If it's the case that the F is injective, then you get the classical state like this. And if you are given G, you get the quantum state like this, where the superposition is there on X register. And if you measure the X register in Adama basis, so here, you measure it in Adama basis, you get D such that D is orthogonal to X0, XORed with X1 equals to 0. Here, this dot represents the inner product. And with a trapdoor, one can invert Y so that you get X or X0 and X1. So and if you stay at this one, it is a little bit similar to the BB84. So to see the similarity, you can consider F as a standard basis position of BB84 and G as a standard basis, G as an Adamar basis position of BB84. And this classical state, X and Y concatenated, is similar to the classical state of the BB84 state. And you can consider this superposition of two preimages as plus state or minus state. They are a little bit similar because you have a superposition of two preimages here. And in the case of BB84, you still have the superposition of 0 and 1. So this seems to be a natural starting point to replace the BB84 state. And furthermore, it has a nice property that we call cut and choose adaptive hardcore property. So NTCF has this nice property. So this property is defined by a game between the adversary and the challenger. At the beginning of the game, the challenger chooses θ1 up to θn, which are random bits. And also choose the functions h1 up to hn so that the hi is chosen from injective function family if θi equals to 0, and it's from 2 to 1 function family if θi equals to 1. And these functions h1 up to hn are sent to the adversary. The adversary doesn't know which position corresponds to the injective mode and which positions correspond to the 2 to 1 mode due to the computational indistinguishability of NTCF. And the adversary submits y1 up to yn to the challenger, and also d1 up to dn. If the adversary is honest somehow, di may correspond to the Adamar basis measurement of the x register corresponding to yi. However, in this security game, the adversary may do something arbitrary. The adversary can do anything that he wants. And after y1 up to yn, d1 up to dn are given to the challenger reveals the basis information, θ1 up to θn, to the adversary. Yeah, it's not the basis, but yeah, you can consider this is a kind of basis information due to the similarity to BB84. Actually, these values, θi, encode the information of hi, whether it is injective or 2 to 1. And the adversary returns x1 up to xn to the challenger. And the cut and choose adaptive hardcore bit property says that the probability of this happening is negligible. And what is this event? It requires that this equation holds. Di times xi0 plus xi1 should be 0 for all I, such that θi equals to 1. So this is basically corresponding to the measurement result of the Adamar basis position in BB84. You have to submit di such that the di is orthogonal to the XOR of the two preimages corresponding to yi. And you also have to satisfy that the f of xy equals to yi for all positions I, such that the θi equals to 0. So it's difficult for the adversary to satisfy these two conditions. That's what the cut and choose adaptive hardcore property says. So again, this is similar to the VRA security. So you can leverage this similarity to achieve SKL, but there are several problems. What is so there is a question: what is di the case in which theta I goes to 0, like what is sent by the adversary. So what the question is, what is di when theta I equals to 0? In that case, di can be anything. You don't check the validity of the di. So there is no valid di because this is just standard basis position. And what happens is that the xi register is just happen to be the classical string in case theta I goes to 0. The X register is a classical string, so if you measure it in the Adama basis, what you get is just a random string. So there is no definition of correct DI for such a position. So this security definition doesn't matter what happens in the DI, what happens for DI in the standard basis position. Okay. Yeah, so this is the security definition, no, security property. And so this is very similar to SKL. So this is a natural starting point. However, there are several problems to overcome. So what is it? Why is it called cut and choose? So basically, the reason why it's called cut and choose is that you hide theta 1 up to theta n somehow. So the adversary doesn't know which part of HI corresponds to standard basis or not standard basis, injective mode or 2-to-1 mode. And even though it doesn't know where what is the hidden theta I information, the adversary should satisfy these two constraints for each of the position. So cut and choose argument, basically, I don't know what is the original usage of this word, but I think that in general, in cut and choose argument, what you do is to check the consistency by inserting something random into random positions, and you run the protocol in parallel, and you check the validity of the operation that the adversary operates on each of the index. Basically, what is happening here is that from the viewpoint of the adversary doesn't know which position is Adama basis position. Intuitively, the adversary's best strategy is to measure the X registers for all the positions in Adama basis to obtain D1 up to Dn. So basically, the idea is that because theta I are hidden from the adversary doesn't know which position. So that basically the idea is that since theta I are completely hidden, computationally hidden from the adversary's viewpoint, the adversary can only measure them in Adama basis. However, in reality, this challenger only checks the DI values for the Adama basis positions. So cut and choose basically refers to the idea of inserting some validity checking point randomly in a hidden manner and check them. So this is I'm not the author of this paper, but I think that this is the reason why they call it cut and choose adaptive hardcore property. Okay. So this is the idea. And so the question is, how can we leverage this property to achieve what we want? So the first problem is that how do we get state that is useful for the for our application. Using the NTCF property, we can compute X concatenated with Y or this state. But to use the proof technique of KMY, what we want is that we extend it into the state like this, namely X concatenated with Y, and you have another register that embeds X into it. Another register that encodes the secret key, which has watermark X. So you want to generate this kind of state. But since you don't have the corresponding quantum channel between the lessor and the lessee, it's not straightforward to send this state directly. Instead, what you want is to do the classical communication in a way that the lessee can be compute this value. So this is the first challenge that we face. And it seems to be useful. It seems to be very similar to the problem of remote state preparation, but the remote state preparation currently requires polynomial number of rounds. And furthermore, this only achieves weak security where the you only have inverse polynomial security. So this doesn't seem to be useful in our application. Another strategy might be to use witness encryption. So why does witness encryption helpful? The reason is that this register X encodes the witness for the this X can be considered as a kind of witness for the statement Y, because f of X equals to Y, which means that X is a preimage of Y. So you can actually, I think that you can actually compute SKX using the witness encryption and some rounds of computation. But in any case, witness encryption is a very strong assumption, and we don't have a good candidate for witness encryption from standard assumptions like LWE. So we don't adopt this solution. And our final solution is to use secure function evaluation. So what is secure function evaluation? Let me explain this in a two-round setting. And for who cares, I omit the common reference string. In our case, we need a common reference string, but for this presentation, I omit it. So basically, two-round secure function evaluation is just the multi-party or not multi-party, two-party computation between a receiver who has an input X and the sender who has an input C. At the beginning of the protocol, the receiver computes the ciphertext that encodes input X using randomness R. So this receiver 1 algorithm computes the ciphertext given an input X and the randomness R. So this is a classical randomness, and this is a classical protocol, but we require post-quantum security. And this can be achieved by LWE. And this ciphertext CT is given to the sender or sent to the sender. And the sender applies some circuit homomorphically, or maybe because of some using some primitive, some mechanism, compute CT prime. You could consider, for example, this ciphertext CT as a FHE ciphertext encrypting X, and the sender algorithm corresponds to the evaluation of the ciphertext and the evaluation circuit C homomorphically. However, our actual instantiation is different, but intuitively, something similar is happening here. So you compute another ciphertext CT prime and send CT prime back to the receiver. And the receiver applies the second receiver algorithm on input CT prime using the randomness R that is used in the first round to recover the value Y. And as a correctness requirement, we require that Y equals to C of X. So this is a correctness requirement. And this is a kind of special two-party computation where we require receiver privacy and the sender's privacy. As a receiver privacy, we require that the sender doesn't learn X. And as a sender privacy, we require that the receiver doesn't learn the information of C. So yeah, here is the secure function evaluation. And we use this as a building block. Do you have any questions? Yeah, so let me explain. So this is the secure function evaluation, and let me explain how to prepare the state by secure function evaluation. So as I explained, NTCF allows the lessee to compute the state like this. So here I omit Y register. So X0 and X1 are going to be the pre-image of Y. And then you apply the secure function evaluation algorithm in superposition like this. So yeah, you have a separate ciphertext register here, and you measure it to obtain the ciphertext. And this ciphertext is sent to the lessor. And lessor may compute something to obtain CT prime. And this CT prime is sent back to the lessee so that this is useful for server to obtain SKXP in superposition. However, this is not immediately possible because, for example, if ciphertext register that is measured here binds to B, then the measurement of this register collapses the quantum state to the classical one. So there is no superposition anymore if the measurement of CT collapses the state. So what we need is that the statistical security for the receiver of the protocol is needed. So in order for this measurement not collapsing the quantum state, original quantum state. So if the quantum state is collapsed into a classical state, then the deletion certificate cannot be computed because it is basically the measurement in Hadamard basis. So what we want is that the measurement doesn't collapse the quantum state. And for this purpose, what we want is that the SFE, the secure function evaluation, has statistical security, meaning that the ciphertext doesn't reveal the information of XP. And we achieve this security. We give an instantiation of SFE satisfying this security requirement. So let me explain how do we compute the state. Again, so you compute this value and measure the register to obtain the ciphertext. So the state is going to be something like this. Actually, I'm here implicitly introducing some additional assumption where the randomness RB is uniquely determined from XP and the ciphertext. But this is not very important here. So this will be important later, but so we have additional assumption here. The randomness RB should be determined from the ciphertext CT and XP uniquely. And this ciphertext is given to the lessor. And this lessor computes the sender algorithm of SFE to obtain the ciphertext CT prime and sends CT prime back to the lessee. Here, the a circuit C is defined so that C of x equals to Sk sub x, where Sk sub x is a watermarked secret key. And using this CT prime, you run the receiver's algorithm in superposition to obtain this state. Here, you use basically the receiver's second algorithm here to obtain the watermarked secret key skxp, which is the computation result of C of x, basically. So you get what you want, but with the additional register RB that encodes the randomness here. So this is how we generate the state that we want. And so this is how do we prepare the quantum state that we want in order to invoke the machinery of KNY25. However, we still have another problem of how can we deal with the security reduction. So what we want is to have a reduction to cut and choose adaptive hardcore bit property. And in the reduction, we have to extract a string D such that D and x0 XORed with x1 should be equal to 0. This is something we want. So to break the cut and choose adaptive hardcore bit property of NTCF. This is what we want. But in the reduction, if we assume an adversary that breaks the SKL property of our construction, what we get is an adversary that outputs C and D such that this equation holds. This is because what you get here is the XP concatenated with an watermarked secret key SK sub XP with additional randomness RB. So due to this additional randomness, what you get is something a little bit different from what we want. So another problem that we have to deal with is to change C and D into another string D star that is orthogonal to x0 XORed with x1. And in order to deal with this problem, we require that the SFE randomness has the following structural property. That is RIB, there is a set of RIB such that this randomness RB can be represented like this. So you can consider capital RIB as a set of matrices, which is indexed by the position and the bit 0 or 1. And this small IB, little RB, is obtained by projecting this set of matrices or set of randomness, depending on the bit, each bit of x0 or x1. So this is the property that we want. And another thing that we want is that we can recover this thing from the trapdoor of SFE. So here is the reduction. Namely, our goal is to get the star that is orthogonal to x0 XORed with x1 from CD satisfying this property. And here we introduce some additional structural property on capital R. The little r. So let me look at the equation. So this is the equation that we have. The adversary chooses C and D satisfying this equation. And we decompose this equation into something like this. So this is just dividing the inner product into some chunks. So here our x0i is the ith bit of x0, and the di is the corresponding bit. And each of R0 and R1 are also decomposed into chunk. And due to the structural property that I require for little r, you can write R0i and R1i like this. Namely, R0 and R1 are obtained by the projection of x0 or x1 onto some set of randomness like this. And in the next step, we write this red value like this. This equation can be seen by inspection. If x0i equals to x1i, then these two values are equal, so this turned out to be 0. But this is the same in the second line, or sorry, the fourth line, actually. Here, the red value is equal to 0 if x0i and x1i are the same. If they are different, what happens is that you get ri0 plus ri1. So this is also the same. So this equation can be seen by inspection. And in the next line, you can see that you can group by x0i plus x1i like this. But here, you have already the desired form. You have d star r, so you can group this value into d star I. And you can write this as a inner product between d star and x0 and XORed with x1. So even though what you can get from the adversary is C and D satisfying these properties, what you finally get is D star that satisfies this final equation. 0 equals to x0 XORed with x1 times D star. So the reduction algorithm outputs D star as its final output. So the reduction works. So this is the technical detail. And so this is the summary. So we construct the first public key encryption with classical-lessor and the VRA security simultaneously for the first time. And we also construct PRF, which is the first one that has classical-lessor. And it additionally achieves VRA security. Similarly, we construct the first digital signature with classical-lessor. And this also comes with the VRA security. And all are from LWE and from the same approach of using combining NTCF with SFE in superposition. And for the reduction, we exploit the structure of SFE so that the proof works. So that's all. Thank you.